Okay, good morning, everyone. Please, I hope you can hear me. Welcome back to another session. Okay, so before we start, please, do you have any questions for me? Any comments, any issues with homework? Once more, if you need help, please feel free to reach out, right? I can meet with you, explain further, do more examples or something. And also, don't forget that your third exam is next week, Friday, right? So, yeah. Be on the lookout for that or start preparing. I've already posted a study guide questions. So yeah, that's it on that. Okay, so if there are no questions, then let's get on to today's work. I'm sharing my screen, no, not a whiteboard, PowerPoint. Okay, I'm sharing my screen at the moment. Please, if you can't see, do let me know. Okay, so the last time, right, we started looking at L'Hopital, right, indeterminate forms and the L'Hopital's rule. Shift. Indeterminate form and the L'Hopital rule, right? So we said that whenever you're trying to evaluate a limit, right? Say a limit as approaches A of a quotient, right? Something divided by another function, a function divided by another function. And then you realize that the limit is giving you this type 0 over 0 or a type infinity over infinity. By the type infinity over infinity, we mean either the numerator is giving you plus or minus infinity, and the denominator is also giving you either a plus or minus infinity, right? So either one. If you notice that that's the case, then you just need to get the derivative of the numerator and get the derivative of the denominator and take the limit, right? The same limit, right? And if that one is going to exist, then that will be the limit of the original function. In other words, the limit of a quotient of functions equal to the limit of the quotient of their derivatives. That's all the L'Hopital rule is about, right? And I was saying that please note that you're not using the quotient rule here. It's not a quotient rule. You're differentiating them separately, right? So, and this one was saying that we have to also note that L'Hopital's rule applies for one-sided limits, right? And limits at infinity as well. So the example that we started doing, and then time our time was up, was this question, example 1. So for this question, when we try to evaluate this limit, I say, okay, let me try plugging in and see. So for this one, ln of 1 is 0, and then 1 minus 1 is 0. So I'm getting 0 over 0. So this type what? 0 over 0. So what do? Well, we employ the L'Hopital's rule, right? So by the L'Hopital's rule, I just differentiate the numerator divided by differentiate the denominator, right? So d over dx of what? Ln of x. We maintain the same limit, and then d over ds of what? X minus 1. Now the derivative of ln of x is 1 over x, and then the derivative of what? X minus 1. That will be the difference rule. So when you differentiate x, you get 1. When you differentiate 1, you get 0. So in the long run, now please, after every step, right? When you differentiate, right? When you differentiate the numerator and the denominator, please simplify, right? If there are any common factors, cancel them out before you proceed. Because the thing is, sometimes if you get common factors and you don't cancel out, you keep getting, let's say you have a type 0 over 0. If you don't cancel out common factors, you keep getting type 0 over 0, and then you keep doing the L'Hopital. But you probably had your answer like steps back ago, right? But because you didn't cancel out or reduce the common factors, you still be doing the type, you still be doing it and be getting type 0 over 0, right? So at each step of the differentiation, at each step of the differentiation, when you differentiate the numerator and the denominator function, see if there are any common factors that you can cancel out. Or if it's a complex fraction, try and see if you can simplify it, right? Before you try plugging in again, right? And then if it also gives you a type 0 over 0 again, you do it again, right? So you keep going and going and going until you get to either an answer. Sometimes you can keep going and you get to something like a non-zero number over 0. Now for that one, you can't apply L'Hopital. You have to use the analyzing thing that we learned way back in chapter 2, right? Okay, so that's it on this one. So when I got here, right, when I differentiated the ln of x, I get 1 over x. When I differentiate the denominator, I get 1, right? So to simplify matters, I get 1 over x. And then I try plugging in again, right? So for this one, for limit as approaches 1 of 1 over x, that's just 1 over 1, which is 1. And this one has no problems. That's my answer, right? So the PowerPoint is just going to give us notes on this solution, right? So first, we know that this is indeterminate form of type 0 over 0. And then you proceed to apply the L'Hopital. So differentiate the numerator divided by the derivative of the denominator. And then you simplify, and then you plug in again. You get your answer. Please, any questions here? Okay. Anybody needs time on this? Okay, then let's do more. Now, there are other kinds of indeterminate stuff, right? So we have indeterminate quotient of type 0 over 0 or type infinity over infinity. There's also something we call an indeterminate product. Now, what is an indeterminate product? Now, for indeterminate product, say you're taking the limit of a product of functions, right? And then you notice that one of the limits is approaching 0, and then the other one is approaching either plus or minus infinity. Now, 0 times infinity or 0 times negative infinity is indeterminate, right? So whenever you have this form, you're trying to evaluate a limit and you get 0 times some kind of infinity, then this is an indeterminate form of type 0 times infinity. Now, as I said, the infinity here is general for plus or minus, right? So if it's 0 times negative infinity, it's still indeterminate form of type 0 times infinity. Now, for this one, how do you solve it? Now, for this one to show this, let me go to the PowerPoint, the whiteboard. I'm sharing the whiteboard now. So if you can't see, do let me know. So this is chapter 4.4. So this is 4.4. And you're looking at indeterminate products. I want to try and explain things here before we look at the PowerPoint. Okay, so for this one, we have limit as s approaches a of f of x times g of x, right? And then suppose you are getting something like 0 times infinity. Right, so let's say that the limit as s approaches a of f is 0, and then the limit as s approaches a of g of s is infinity. Now, whenever you have this case, there are 2 ways you can go to get the solution. One way will be the valid one. The other one will just be a distraction. But let's try and explain how you'll be able to figure out the valid one, right? So there are 2 ways. Now, the thing is, whenever you have an indeterminate product, you try and rewrite it so that it becomes something like an indeterminate quotient of type 0 over 0 or type infinity over infinity. Now, to do that, recall that if you have, say, let me make this note. So note, if you have, say, a times b, well, it's the same as what? A over 1 over b. And it's also the same as b over 1 over a, right? So this a times b is the same as 1 divided by a over b, and it's the same as b divided by what? 1 over a, right? So with this algebra in mind, we can say that, okay, now for this limit, we can express this. So there are 2 ways, right? You can say approach 1. You can transform this product into what? Either you keep the f of x up here, and then you move the g of x as 1 over g of x. Now, what is the motivation? Why would we want to do this? Well, when you rewrite it in this form, let's see what this limit becomes. Now, the function is like a quotient. It's no longer a product, right? It's f of x over 1 over g of x. So this is one function. This is one function. This is another function. The 1 over g of x is another function. Okay. So now, with that said, let's try and see what this limit will give us. So now, for this one, look at this. We are saying that the limit as s approaches a of f of x is, this one is giving us 0, right? And then this one is giving us infinity. Okay. So now, if that's the case, then when we write it in this form, right, then the limit as s approaches a of f of x, that will give us what? 0. Because the limit as s approaches a of f of x is 0. Now, what about this one, the denominator? The denominator is 1 over g of s. Now, we know that g of s approaches infinity, right, as s approaches a. So that means 1 over g of s will approach what? What's 1 over infinity? Anybody? What's 1 over infinity? Let me see. I think I see. Perfect. It's 0. Thank you. It's 0, right? So what does this reduce to? Now, first, it was an indeterminate product, 0 times infinity, but because we made this transformation, it has become what? An indeterminate form of type 0 over 0. And then we apply what? L'Hopital. So we differentiate the f of s, differentiate the 1 over g of s, and keep going until you get your answer, right? So it reverts to the original problem that we started with. Now, another way you could have done this is, instead of leaving the f of x on top, not approach 1, approach 2. Right, we could have left the g of x also on top. So this is the same as g of x on top here, and then all over 1 over f of x. Now, when we write it in this form, what are we getting? Well, we know that the limit as s approaches a of g of s is infinity. So that means the top is some kind of infinity. Now, what about the denominator? The denominator is 1 over 0. 1 over 0. Now, 1 over 0 is a non-zero number over 0. You see? So that means your answer is either going to be either a plus infinity or minus infinity. But in either case, you are going to end up with what? A type infinity over infinity indeterminate form. You see? So it has also, if you write it in this form too, it reverts back to the what? That indeterminate form. So we apply L'Hopital, differentiate the g of s, differentiate the 1 over f of x, and then try and get your result. Right? So that's the strategy. But as I was saying, only one approach will work. Now, how do you figure out which approach to use? How do you figure out whether I'm leaving the f of s on top or leaving the g of s on top, right? So I'll say this. No matter the approach that you use, right, when you apply the L'Hopital, it should give you a much simplified expression than what you started with, or the previous steps expression, right? So I say the approach to use should not lead to a more complicated expression than what we currently have. That's the trick. How to know which one to pick, right? So I'll explain more about this. What I mean by the approach should not lead to a more complicated expression than what you currently have, right? So this is how we do it when we have indeterminate product. Please, any questions here? Okay. So let me wait for some seconds and then I'll move on. Yeah. Okay. Anybody still needs time here? Okay. So let me share the PowerPoint and look at the example that we have, and then we can move on. So this is just talking about what I just said, right? So it can go 2 ways. F times g of s, you can rewrite it as what? F over 1 over g, or you can rewrite it as what? G over 1 over f. Now this will convert it to type 0 over 0 or type infinity over infinity. So you can use the L'Hopital's rule. So let's look at example 6, right? So x ln of x. So for that one, we have limit as s approaches 0 from the right, x ln of x. Okay, so now let's try and find this limit. So we said, okay, so let me try say plugging in and see. Now for the first one, right, for x, the limit as s approaches 0 from the right of x, that one is going to give us 0. Now what about this one, the ln of x? Well, if you recall, right, for ln of x function, this is how it behaves. At 1, it is 0, right? And then as it approaches 0, it's approaching in negative infinity like so. It's like this. This ln of x, right? So that means for this one, for the ln of x as s approaches 0 from the right, that one is going to be what? Negative infinity. So this is what? 0 times negative infinity. That means it's an indeterminate product. It's an indeterminate product. So you say, okay, for an indeterminate product, what should I do? Okay, there are 2 ways, right? I have to identify the 2 functions involved here. The 2 functions are x and ln of x, right? S and ln of x. Okay, so now the thing is, I have to leave one on top and then move one to the denominator. Now let me add this comment. Now, the more you practice this, you'll be able to identify what to move down and what to leave up, so that you don't pick the more complicated route, right? But let's start by building our experience here. Now, the thing is, whenever you have ln of something and another expression, it's always likely that you have to move that other expression down, right? So as I was saying, you are building experience. So whenever it's ln of something and then another thing, always move leave the ln of s on top and move the other expression down, right? That's likely a better course, right? So now let's see if we didn't know this, right? If you didn't know this, what are you going to try? Okay, so we say, okay, now I need to leave one on top and then move the other one down. So let me start with the correct approach, right? Let me start with a correct approach. So I'll say, okay, I need to leave one on top. So this is the correct approach. So what do I do? Okay, let me leave ln of x on top and then let me move x down. I've not changed the expression. It's still the same thing, right? But in rewriting in this form, I've been able to obtain what? An indeterminate quotient. Now for this one, it's going to be, the top is going to give me negative infinity. The denominator, 1 over x as s approaches 0 from the right is what? Is positive infinity. So we don't even need to check for this because whenever it's an indeterminate product and you write it, you transform it in that form, it will always give you that type 0 over 0 or type infinity over infinity. So you can just immediately transform, just apply L'Hopital, right? You can just apply L'Hopital. So here, let's apply L'Hopital. So applying L'Hopital, what we have to do is, let's get the derivative of ln of s. Can you please help me with that? What's the derivative of ln of s? Somebody. What's the derivative of ln of x? And then I need to do the derivative of 1 over x. Thank you, thank you. Let me see, I see some comments in the chat. Okay, perfect. It's 1 over x. Thank you, awesome, right? And then please, what about the derivative of 1 over x? The denominator one. So I have limit as s approaches 0 from the right of that. You said the top is 1 over x. Okay, I have 1, yes, I have a seconder, but still try again. Let's see. Negative x over s squared. Try again. You are close, very close. This time, you guys, you've seen a lot of this, so I want you to get this right. So please try. I don't see the answer yet. I don't see the answer. Wait. Oh no. Okay, I don't see the answer yet. Close. Negative x. Oh no, what's happening? Sometimes just. Okay, I don't see it yet. Somebody, can you try? Anybody? What's the derivative of 1 over x? Negative 1, close, still close. The derivative of 1 over x. Have you guys forgotten? Okay, then let me just say it. The derivative of 1 over s is negative 1 over s squared. Yeah, oh yeah, thanks. You just gave it to me just as I wrote it down. Thank you. Yeah, that's correct. So oh yeah, and one more thing, please try and see if you can comment so that everyone in the group can see, right? Comment so that everyone in the group, because I see direct messages. I don't know whether it's the system has automatically reverted to direct messages or something. So please send it to, oh, okay, I see. Everyone publicly. Yeah, I see. It's not I didn't do that setting. Sometimes it just goes back. Everyone publicly. Yeah, I think this will make it work. Okay, so yeah, I just saw that. I don't know why it does that. No one. Okay, so thank you, right? So let's move on. Now, we have 1 over s over negative 1 over s squared. Now, as I said, whenever you differentiate, right, simplify before you move on. Don't keep plugging in and keep differentiating, right? So at this step, I see 1 over x divided by negative 1 over s squared. So for that one, let me show you this trick I always use. Whenever I have 1 over b over c over d, this complex fraction, you can always just obtain it very easily by taking the d to multiply what? This. So it's more like the ends will multiply and then the closer ones here will also multiply, right? So you end up getting AD over BC. Very simple way of looking at these complex fractions. So for this one, I'll say, okay, this one is just going to be simplifying this. I can move the s squared on top. So s squared times 1, that's s squared. And then x times negative 1, that's negative x, right? Now I can cancel out common factors. So that'll give me limit as s approaches 0 from the right of what? Negative x. And then at this point, I've simplified it. So I plug in again, right? So I try plugging in. So that'll give me what? That just give me 0. And that's my answer, right? Okay. Please, are you okay with this step? Is there any part you don't understand? Any questions? Okay, then let's proceed. Now, this is the correct approach, right? But what if we didn't know and we took the other route? So I'm going to show you what it looks like when you made a mistake, right? When you took the wrong route. Because for product, indeterminate product, we know we have two ways. We have to see the other way too when we make a mistake. So let me say wrong approach. Now you see why this is a wrong approach. So this is limit access approaches 0 from the right of x ln of x. So for the wrong approach, I'll say, okay, now I still identify the two functions, it's x and ln of x. So I'll say, okay, now let me just leave the x on top and then divide by what? 1 over ln of x, right? Now for this one, you end up with type 0 over 0. But then the thing is, because it's type 0 over 0, we can employ the L'Hopital's rule, right? So L'Hopital. So just differentiate the numerator. So that's this. Differentiate the numerator, divide by the derivative of the denominator. Okay, now for this one, the derivative of x, that one is straightforward. We have the derivative of x is just 1. Now the derivative of 1 over ln of x, that one is going to be the same as d over dx of ln of x all to the -1. So you have to employ the chain rule. So by the chain rule, let me circle this and do it on the side. By the chain rule, I'm getting differentiate the outer function. So that'll be -1, and then plug in the inner function, ln of x to the -2 times the derivative of the inner function. So that's over x. The derivative of ln of x is 1 over x. So like so. So that means that you have something like limit as x approaches 0 from the right of 1 over what? Negative. Okay, so you can make it, yeah. So 1 over, let me simplify it a bit. So you have 1 over, so you have -1 over x and then ln of x all squared, something like this, right? So that's this. But the thing is, this expression you have here is more complicated than what you started with, right? We started with this one. We started with this, the x over 1 over ln of x. Now the ln of x down here is even squared. That means it's even much more, it's worse than what we started with, right? We want it to simplify as we go, not become more complicated as we go, right? So this one is more complicated. So immediately you take this step and you get the expression, which is more complicated than the expression you had in the original step before you took this. Then you say, okay, I know that this is not the route to take. So not the right. Right. So that's how it will look like when you made a mistake and moved the wrong expression down and left the wrong expression up. Right. So that's the indeterminate product. Please, any questions here? I hope you understand this. Okay. Then let's move on. Oh, anybody needs time on this? Okay. So that's how it will look like when you made a mistake. Now, this is just going to give us the solution to what we just talked about. Right. So that's the first factor, 0. And then you can do this, leave the ln on top, you get 0 nicely. Like another possible option would have been to do this, right? Leave the s on top, divide by this, but it will give you, so that won't give you an indeterminate form of type 0 over 0. But when you apply the L'Hopital, you get a more complicated expression than the one you started with. So that means that's not the route to take, right? So that's it. Right? So in general, we always choose the one which will lead to what? A simpler limit than what we started with. Okay, now let's move on to another indeterminate form. This was called indeterminate differences, right? Indeterminate differences. Now for indeterminate differences, you're taking the limit of a difference of functions, but then you end up with one of them approaching infinity and the other one approaching negative infinity, right? So if you end up with something like infinity minus infinity, infinity minus infinity is indeterminate. It's indeterminate. It's not 0. right? Because for those two infinities, maybe one function is increasing faster than the other one, right? The second one, in which case that will make it infinity, or the second one is increasing faster than the first one, which will make it negative infinity, or the two are kind of like close, are increasing close together, which will make it a constant. So you can't really tell, right, that this is zero. That's why it's an indeterminate form, right? So for this one, this form is either you are getting something like infinity minus infinity, or say negative infinity plus infinity. So in either case, this will be an indeterminate difference. Now for indeterminate difference, the way to go is, there are three ways, right? If you have an indeterminate difference and it involves quotients, right? A function over a function, say minus another function over a function, then what you're going to try to do is, you're going to try to what? Write it as a single quotient, right? So that's what the sentence says, convert the difference into a quotient, right? So if it's a function over a function minus a function over a function, and then it's giving you infinity minus infinity, then try and combine them and write it as a single function. Now, when you combine them, it will now become an indeterminate quotient of type 0 over 0 or type infinity over infinity, and then you employ L'Hopital, right? So that's the first case. The second case is if it's a radical, if it contains a radical, right? And then you get some type infinity minus infinity or negative infinity plus infinity, then what you have to do is you rationalize, right? So that's why this one says you rationalize. You see, you rationalize. The first one was right as a single quotient by finding a common denominator. That's what I talked about. Now, the third one is if it's not a quotient and it doesn't contain a radical, but then you can factor, right? If you can factor it, then that's the way to go, right? So in general, you're just trying to see if you can simplify the thing, whichever simplification comes naturally, and then try and employ L'Hopital, right? Somewhere down the line. So that's the goal. So three ways, three possible cases, right? So either you are getting some quotients, difference of quotients, in which case you combine them and write it as a single quotient, or it involves radicals, in which case you rationalize, or it involves what? It doesn't involve a radical, or it's not a difference of quotient, in which case you try and factor some common factor. Do you see? Yeah, so those are the three cases for indeterminate difference. Now let's move on and see an example on this. Please, any questions so far? Okay, so now let's look at example 7. This one has a solution here, so let me do it on a whiteboard. So for example 7, so for that one, I have limit as s approaches 1 from the right of 1 over ln of x, and then minus 1 over s minus 1. Okay, so for this one, let's try and see what the limit will be. So I say, okay, now for this one, I see 1 over ln of x. So what is that limit going to approach? So, okay, I say, okay, for ln of x, it's always a good idea to see the graph, right? So for ln of x, I have 1 here, it touches 1 here, and then it goes like so. And then it goes down, approaching negative infinity as you approach 0. Okay, so now, this one is 1 over ln of x. Now, when you plug the 1 in, you get 1 over ln of 1, but ln of 1 is 0, so that one is 1 over 0. Now, 1 over 0 is a non-zero number over 0, so that means your answer for one-sided limit is either going to be plus infinity or negative infinity. You see? So the thing is, which part of 0 is the denominator approaching from? Is it like something like a 0.00001 or a negative 0.0001? Well, as you can see from the graph of ln of x, right, as you approach from the right of 1, from this side, from this direction, then it is in the positive region. So that means that it's approaching 0 from the right. So it's something like 0.00001 of some sort. So that means 1 over 0.00001, that's going to give us what? Infinity. Now, what about the second part? For that one too, if you plug 1 in, you get 1 over 0. Okay, so it's a non-zero number over 0. So for one-sided limits, that means you're going to get either a minus infinity or a positive infinity, right? But then this one is approaching 1 from the right. So it's taking on numbers like 1.00001. But 1.00001 minus 1, that will give us a positive 0.0001. And then 1 divided by the positive 0.001 is going to give us what? Infinity. Nice. Now, infinity minus infinity is what we just talked about. It's an indeterminate difference. It's an indeterminate difference. So the question I should ask is, does this contain a radical? No, it doesn't contain a radical. Is this a difference of quotients of functions? Well, as you can see, this one is like a function over a function minus another function over a function. So we can, in fact, write this using a common denominator and write this as a single quotient. So that's the first route, right? So that's the way we will go, right? So because it's what? Something divided by something and then minus another quotient, then you can write this as a single quotient. If it contains a radical, you rationalize. If it doesn't contain, if it's not a quotient, a difference of quotients, or it doesn't contain a radical, then you try and factor. So there are three ways, right? So for this one, you go, they're writing it as a single quotient route, right? Because it involves a difference of quotients. So let's first get an LCD. So for this one, the LCD will just be x minus 1 ln of x, right? So let's try and write this as a single quotient. So we're going to have limit as s approaches 1 from the right. And then for this, I have x minus 1, and then s minus 1 down here, and then ln of x. And then minus, for the second part, I have 1 times ln of x over, we already have s minus 1, and then ln of x. Right, so now I have a common denominator, so I can write it as a single quotient by just subtracting the numerator. So I have x minus 1 minus ln of x, and then all over the denominator is just s minus 1 ln of x. Now, you will see that if you try and what? Analyze this limit again, this time around, it's not going to be an indeterminate difference, but it will always end up, you always end up with either a type 0 over 0 or type infinity over infinity, so that you can employ the L'Hopital's rule again, right? So to verify that, let's just check it, since we are just doing this example for this one. So if I plug in 1, I get 1 minus 1, right, which is 0, and then ln of 1 is also 0, so the numerator is 0. What about the denominator? If I plug 1 in here, I get 1 minus 1, which is 0, and then ln of 1 is 0. So we have 0 times 0, which is also 0. You see, we have an indeterminate form of type 0 over 0. So we apply L'Hopital. So applying the L'Hopital, let's differentiate the numerator expression, right? So the derivative of x is 1, the derivative of 1 is 0, the derivative of ln of x is what? Is 1 over x. So we have it like this. Now for the denominator, I can employ the product rule here, because this is a product of functions, right? So by the product rule, differentiate, leave the first function, differentiate the second function, plus leave the second function, differentiate what? The first function. That'll be 1, right? Now, when you get here, as I said, if it's a complex fraction, try and simplify it, right? The way I can simplify this expression is, I have x as a common denominator, so I can multiply both the top and the bottom by x. I haven't changed the expression because s cancels x, right? So in doing this, I'll be able to simplify it. So I'll have limit as s approaches 1 from the right. Now s times 1 is x, and then s times 1 over s is 1, right? And then all over. Now x times x minus 1 times 1 over s, the x's will cancel, so that'll leave me with s minus 1 for the first term. And then plus, for the second part, I have x ln of x. Please, I hope you follow. Any questions so far? Okay. Now, when you get here, we've simplified, right? So we try plugging in again. When you plug in again, you have 1 minus 1 on the numerator. That'll give you 0, right? 1 minus 1 here will give you 0. And then 1 times ln of 1, which is 0, will also give you 0. So you still have type 0 over 0 again. As long as you keep getting type 0 over 0 or type infinity over infinity, you will keep on applying the L'Hopital. So let's apply the L'Hopital again. So this time I'll differentiate the x minus 1. The derivative of x is 1. The derivative of 1 is 0. So I get 1 for the numerator. The derivative of x is 1. The derivative of 1 is 0. And the derivative of x ln of x, that one is leave the first one, differentiate the second one, right? The derivative of ln of x is what? Is 1 over x. Plus leave the second one, differentiate the first one, and then the derivative of x is 1. Please, are you okay so far? Any questions? Anybody needs time on this slide? Okay. So now let's move on, right? So simplifying methods, I think the s's will cancel out down here. So I'll have something like limits The L'Hopital can be something, you know, sometimes you can go like about 3 steps before you get your answer. S approaching 1 from the right. And then the numerator is just 1 on top. And then the denominator is, this one is 1. And then the S's will cancel. So that'll give us 1, right? So 1 plus 1 is 2. So 2 plus ln of x. So this is where we are now. Now for this one, we don't have any common factors to cancel out. So we just try plugging, right? So we end up with 1 over 2 plus ln of 1. But ln of 1 is 0. So that one, we got 1 over 2. We didn't get 0 over 0 again. This one is perfect, right? No problems. So that's our answer. Please, are you okay with this? Any questions? Is there any part you don't understand that you want me to go over? So that's an indeterminate difference. Anybody needs time here? So we are going to have a nice solution on the PowerPoint, right? So it's going to explain it step by step like I did. Okay, and then we get this. Try 0 over 0 again, do it again, you get this. Plug in and get 1 over 2. Now, the last thing we're going to look at, indeterminate powers. Indeterminate powers. So for indeterminate powers, you are trying to take the limits as S approaches A of a base function to some power, right? Which is also a function. And then you end up with these 3 cases. Either you are getting type 0 over 0 to the power 0, right? So the base function is approaching 0. The exponent function is approaching 0. So that's 0 to the power 0. The 0 to the power 0 is indeterminate. Or the base function is approaching infinity, some kind of infinity. It could be negative infinity or positive infinity. And then the exponent function is approaching 0. So that's our type infinity over infinity to the power 0. Or the last one is the base function is 1. It's approaching 1. And then the exponent function is approaching infinity. So please don't be tempted to say that 1 to the power infinity is 1. It is not 1, right? 1 to the power infinity is indeterminate, right? But maybe let me ask this. What is 0 to the power infinity? I think you get a question like that on your homework. What is 0 to the power infinity? Anybody? 0. Okay, 0, 1. Okay, so 0 to the power infinity is 0, right? Is 0. That one is 0. But 1 to the power infinity is indeterminate. Okay, so when you get either of these forms, right? And don't forget that for whatever the infinity is, it could be negative infinity too, right? Then that means you have an indeterminate power, right? An indeterminate power. Okay, so now let's see. Let's look at an example. Now for this one, how do you solve it? Let me show you how we're going to solve it before we look at example. So let me say indeterminate power. Indeterminate powers. So for this, we have this. And then you are getting either some kind of 1 to the power, either plus or minus infinity, or infinity to the power 0, or what was the last one? 0 to the power 0, right? Either case, then it's an indeterminate power. So how do we solve this? Well, to solve this, remember that if you have, so let me say, note, if you have e to the ln of, say, a, then the exponent, and then if you have an e and then to the power log of the same base, right? If the bases match, then your answer is just a, right? So if you have f of x to the power g of x, then we can rewrite this as what? E to the what? Ln of what? F of x to the power g of x. Right? We can write it as this. Now, another thing you have to also note is whenever you have ln of a base to some power, then it's just equal to what? The power times ln of the base. Right? So with this expression, if you have f of x to the power g of x, then we can rewrite that as what? E to the power g of x, and then ln of what? F of x. Okay, so if that makes sense, then let's look at, now let's come back here, right, to the limit. So that means if you have the limit as s approaches a of f of x to the power g of x, then that's the same as what? The limit as s approaches a of what? E to the power what? G of x, and then ln of what? F of x. Right. Now, the thing is, the exponential function is continuous everywhere. So by continuity, remember that if you have a continuous function, then you can just take the limit of what is inside the inner function and then apply the outer function on the value that you get. So that means for this one, the limit as s approaches a of e to some power is just equal to what? E to the power the limit. So just take the limit of what is the inner function, which is the exponent here. Right? Don't forget that for exponential function, the inner function is in there, it's up there, it's in the power. Right? So the limit as g of x, ln of f of x. Now, the thing is, you shouldn't be deriving, okay, it's up to you. You can decide to derive this on the exam, but it's not advisable, right? Because of time constraints. So you have to just know this or memorize this, right? That whenever you have an indeterminate power, the answer will just be e to the what? Limit, the same limit, and then the exponent function first, multiplied by what? The natural log of the base function, right? So this is something to note. I should just note this. Let me circle it in blue. Right, so this is important for indeterminate powers. Right, so just note this. Please, any part of the derivation that you don't understand, that you want me to explain again. Okay. Anybody needs time here? Okay, so now with that said, let's go back to the PowerPoint, right? So just going to talk about what the derivation. So there's the derivation we get here. Now, one important thing you have to notice, the motivation why we do that is, now, when you get e to the ln of, when you get, say, limit as s approaches a of f of x to the g of x, then we say we can write that as what? E to the limit as s approaches a of what? G of x times what? Ln of f of x. So for this one, why do we do this? Now, just focus in the numerator. Let's look at each of the cases. So the cases are type 0, 0 to the power 0, infinity to the power 0, and then 1 to some kind of infinity. Let's say positive infinity, right? Plus or minus infinity. Now, the thing is, so this one, the g of s are always the exponents, right? So if you have limit as s approaches a of g of s and then ln of f of s, if you consider the type 0, 0 to the power 0, then the g of s will be what? 0, right? And then the limit for the limit as s approaches a of ln of the base, which will also be approaching 0. That one, for ln approaching 0, that one is going to approach negative infinity. That means that one will lead to what? If a 0 times 0, it will lead to what? A 0 times some kind of infinity. It will lead to type 0 times infinity. Now let's consider the second case. If it's infinity to the power 0, then considering the limit as s approaches 0 of g of x and then ln of f of x, the g of x will also be approaching 0. Right? Still, it will be approaching 0. What about the ln of the base? Now, ln of s will approach infinity as x approaches infinity. So if the base is approaching infinity, then the ln of that base will also be approaching infinity. So it still gives you type 0 times infinity. What about the third case? Now, for the third case, the g of s is up here, right? It's approaching some kind of infinity, either plus or minus infinity. So for limit as s approaches 0 of g of s times ln of s, the g of s will also be approaching infinity, right? It could be plus or minus, right? Now, what about ln of the base? Now, because the base is approaching 1, ln of 1 is 0. So the point I want to emphasize is, in either of the three cases that we saw here, for all these types, whenever you transform it into e to the power, g of s times ln of s, and you take the limit of the power here, then it's always the limit of the power here will always become an indeterminate product. It becomes an indeterminate product, and then we know how to solve for indeterminate product, right? The indeterminate product can now be transformed to what? An indeterminate quotient of type 0 over 0 or infinity over infinity, and then you apply L'Hopital again. So all of this is kind of like it reverses back. You see, it reverses back to the original L'Hopital condition, and then you apply L'Hopital, right? So that's one thing you have to note. So that's why this is saying, in either method, we are led to the indeterminate product, right? G of s times ln of f of s, which is what? 0 times infinity. Okay. Now, with that said, let's look at an example. Example 9. Okay, so for this, we have limit as s approaches 0 from the right of 1 plus sine of what? 4x all to the power cotangent of x. Okay, so now let's try and see what this limit is. So for the first case, right, we look at plugging the 0 in, right? For the denominator, you see that when you plug it in the denominator, you get, let me use a different color here, right? Sine of 4 times 0. 4 times 0 is 0. Sine of 0 is 0. 1 plus 0 is 1. Now, what about the power here? Now, for the power here, cotangent of x. Okay, for cotangent of x, we know that cotangent is the same as what? Cosine over sine. Right? So note that cotangent of x is the same as what? Cosine over sine. Now, as s approaches 0, right, from the right, the cosine will approach 1. And then the denominator, sine will also be approaching 1, 0. Sine of 0 is 0. Now, because it's 1 over 0, that means you're going to end up, and it's one-sided, you're going to end up with either a plus or minus infinity, one of them. We don't really care, because as long as it's either of the infinity values, we have at what? An indeterminate power. We have an indeterminate power, right? An indeterminate power. Okay, so now because we know we have an indeterminate power, we just click. Okay, so what's the formula to use? So the formula to use is this limit that we have here. Will then become what? E to the what? Write the limit again, the same limit. The exponent function, cotangent of x. And then what else? And then what? The ln of what? The base function. The base function is 1 plus sine of what? 4x. Right, so that's it. You have this setup. So what you can do is you can just focus on what? Just the power here, and then get the limit. And then when you are done, you just fix the answer as a power of e. So let's just focus on that. So let me just do this. So limit as s approaches 0 from the right of cotangent of x, ln of what? 1 plus sine of 4x. Okay. So now I know I don't even have to check for this limit, because I know that it will always lead to an indeterminate product. It will always lead to an indeterminate product. For indeterminate product, you have to leave one function on top and move the other one down, right? And as I said, whenever ln meets with another function, right, it's always likely that the ln has to stay on top, right? So I'll leave the ln here. And then do 1 over cotangent of x. Please, are you okay up to this point? But 1 over cotangent of x is the same as tangent of x, right? 1 over cotangent of x is the same as tangent of x. I'll have to continue on the next slide. Do let me know if you need more time. Okay. So that means that we have limits as s approaches 0 from the right of this cotangent of x, and then 1 plus sine of what? 4x. We now have, we are now looking at limit as s approaches 0 from the right of, this ln of this ln. So we have ln of what? 1 plus sine of 4x. And then all over what? Tangent of x. So this one is going to be what? Now type 0 over 0 or type infinity over infinity. If you plug in 0 here, sine of 0 is 0. So you get ln of 1. So that's just ln of 1 is 0. If you plug 0 here, tan of 0 is 0. So you see type 0 over 0. So employ L'Hopital. So to employ L'Hopital, you have to do what? The derivative of the numerator function. 1 plus sine of 4x. Over what? The derivative of the denominator function. So tangent of x. So we have this. Now for the top, we are differentiating ln of something, right? So you can employ the chain rule, or you can employ the rule about the ln being the outer function. So just differentiate the function, divide by itself. So the derivative of 1 is 0, the derivative of sine of 4x by the chain rule is 4 cosine of 4x. And then divide by the function itself. So that's 1 plus what sine of what 4x. The derivative of tangent is what secant squared of x. Right. So simplifying things here. This one is long. Okay. It's almost, yeah, it's 50. Let me just finish this. Yeah, we are done. We are almost done. So let me finish this and then that'll be it. But please, do you need more time here? Okay, so then let me move on. So the limit becomes limit as s approaches 0 from the right. We have 4 cosine of what? 4 cosine of 4x. And then over, when you simplify, it's just going to be 1 plus sine of 4x. And then secant squared of x. So this is it as a single quotient. Yeah. And then you plug in again. So 4 times 0 is 0. So cosine of 0 is 1. So you get 4. Sine of 0 is 0. 1 plus 0 is 1. Secant of 0. Secant of 0 is 1. Right? So 1 squared is 1. So you get 1. So you get 4. But don't forget that 4 is not your final answer. 4 is just the exponent, the limit for the exponent here. Right? So your final answer will then become what? That's the conclusion. Your final answer. Limit as s approaches 0 from the right of 1 plus sine of 4x to the power cotangent of x. It's now going to be what? E to the power 4. And that's your answer. Okay, and that'll be it for today. Thank you very much for your time. Yeah, all the best. Please feel free to reach out if you don't understand anything, right? Don't wait for it to pile out because you have an exam coming up soon. So yeah, so see you on Friday. And tomorrow, on tomorrow's quiz, I think you'll be having, I'll give you a function and you have to do all like, find it, use the ID test, use the first derivative test, get concavity, and then do like a point of inflection. So that's what to expect on tomorrow's quiz. Yeah, so all the best. See you on Friday, as I said. Thank you. You are welcome. You are welcome, Daniel. Daniel, you're welcome.